Hello, and welcome back to our second video of the bite-sized integral calculus series where we are helping you to get a better grasp of what first year integral calculus is and how you can score great marks in your first year math integral calculus level courses as well. So in this video we'll be covering a basic overview of what we did in the last video and sort of reinforce those ideas by doing some simpler examples and how we can use those concepts of integration that we learned in the last video and how we can apply those concepts of integration based on the examples that we'll do in this video. So let's start the video with a basic overview of what we did in the last video. We talked about the basic definition of integration, which is basically about calculating the area under the curve. So if you have a function y equals fx on a graph, if you have a curve on a graph and you have to integrate that function or the curve, you just have to calculate the area under the curve. That is what we discussed about integration and the definition of integration in the last video. So in this video, we'll be continuing on that topic and we'll be doing some similar examples or some examples which will reinforce the idea of integration as the area under the curve. So I'll be talking about some basic examples, and as you can see on the screen as well, on the right hand side, I'll also give you the solution of what integration gives you and how we can sort of use that existing formula or that existing answer that we have for the integration of that function or the curve, and how we can relate that existing answer to the area under the curve definition that we have for integration right now. So we'll start with the most basic curve that we have in our math level integral calculus course, which is fx equals to c, where c is a constant, c is a real number. C can be anything, C can be 1, can be 2, 3, 568, minus 24. It can also be a decimal value. So it's basically C is a constant which is a real number. And now the first basic example is to calculate the integration of fx equals c, the integration of the curve which represents y equals c. So now in this example we'll be covering how to integrate fx equals to c by only using the definition of area under the curve and not relying on the answers or the basic formulas that we have for integration. So as you can see on the screen, the integration of c, I've also written the answer on the right hand side of the screen as well. So the integration of c, fx equals to c, is basically c times the width of the interval that we are taking. So let's consider this graph. Let's start with fx equals to c function. So we have fx equals to c, and let's create a graph of that function. Let's do the curve sketching and see how fx equals to c would look like. So we have fx equals c, where c is basically a real number. Let's consider arbitrarily that c is positive. It can also be applied to the negative values of c, but in this example only we are taking c to be positive just for the sake of simplicity in this example. So in this example we can see that we have just taken, for the sake of simplicity, c to be greater than 0. So fx equals to c would somewhat look like this, where this point is c on the y-axis, right? So, and for example, if we have to, now we have to integrate fx equals to c function, right? So we'll take a basic interval. So integration is basically of two types. One is indefinite integration, where you don't take an interval. The second one is definite integration, where we take an interval to sort of calculate the integration of that function. So in this example, basically, in order to simplify this question, we'll take the integration of fx equals to c from x equals 0 to just x equals 2. So we see this is x equals 0 and this is x equals 2, for example. Now in order to calculate the integration of fx equals c by only taking the definition of area under the curve, what do you think the answer would be? In this case, it's obvious that since it's forming a rectangle, the area under the curve for fx equals to c in this case would only be base times height, right? So in this case, since the base is 2, which can also be represented as 2 minus 0, and the height is c, so now the answer of fx equals to c, when we are taking the integration of fx equals to c from x equals 0 to 2, becomes c times 2. And we can also confirm this answer based on the existing answer that we calculated in our fx equals to c integration, which was c times 2. So now since we confirmed our answer to be the same as the existing answer that we have for the integration of c, it sort of serves as a reinforcement for us that integration is indeed the area under the curve. Now we will move on to the second example that we have on the screen, which is fx equals to x. We'll sort of follow the same process what we did in the last example. We'll sketch the graph. So the graph sketch would look somewhat like this, where you have the y-axis and you have the x-axis. And since your graph is fx equals x, you'll just write this. You'll have a line which is inclined at a 45-degree angle to the x-axis, right? So in this example, we'll take the same case from x equals 0 to x equals 2. And we also know from the existing definition, from the existing answer of integration of x, that it's x squared by 2, as you can see on the right hand side of the screen. And we just have to confirm the existing formula of integration of x is x squared by 2 by confirming it with the formula that we'll derive in this question. So this is the function, and since we are calculating from x equals 0 to x equals 2, this is x equals 0 point, and let's say it's x equals 2, and you have to calculate the area under the curve. And now as you can see in this example as well, the area under the curve is basically the area of the rectangle which is enclosed by the curve from x equals 0 to x equals 2. And since in this case it's a right angle triangle, the formula of the area under the curve, or the area of the triangle in this case, becomes half times base into height, which in this case the base is 2 and the height is 2 as well, because it's y equals x, so the height will also be 2, which appears to be 2 square upon 2, which is the same as the answer that we have on the screen. We just have to substitute the value of x equals 2 in this case, and we'll get the answer, which sort of serves as a confirmation or a reinforcement of the existing idea of integration that we have right now as well. So these were some basic examples which sort of reinforces your idea of integration as the area under the curve, and how you can calculate or how you can integrate some certain curves by only sketching those curves and calculating the area under those curves. So that was it for today's video. At the very end of this video, I'll leave you with a challenging question, and I would really appreciate if you can comment down in this video of what you feel the answer of this question would be. In order to solve this question, I would highly suggest you to first sketch the graph of this function, and when you'll sketch the graph of this function, you'll see that the integration of this function would be just calculating the area of a very similar shape that you know in math. So that was a hint from my side. I hope it helps. You can also comment down in the video if you have any doubts related to this video or related to this challenging question as well, and I'll make sure that I reply to your comment as soon as possible. So thank you so much for watching. I hope you really liked it. Please follow the channel in order to be notified of the videos that I'll be uploading next, and stay tuned. Thank you.